Hi everyone, I am Elisa Nonni and today I will discuss the modeling of mixed phases in methylammonium lead iodide or MAPbI3. I will introduce the MAPbI3 physical structure and the motivation of this work, the device modeling and maps generation algorithm. I will show the parameter settings and discuss the results of this study. MAPbI3 has gained an increasing success due to its electro-optical properties such as excellent carrier mobility and high defect tolerance, along with low cost and simple preparation process, to name a few. This perovskite is characterized by a methylammonium organic cation, a lead metal cation, and a iodide halogen anion, and it shows a cubic phase for temperatures above 330 Kelvin, a tetragonal phase between 330 and 163 Kelvin, and an orthorhombic phase for temperatures below 163. And each of these phases shows different energy gaps, lattice constants, and mobility and permittivity parameters. This work investigates the resistivity behavior in MAPbI3, since photoluminescence and X-ray diffraction or XRD experiments highlight that the phase transition between tetragonal and orthorhombic phases occur gradually. This plot here shows the resistivity as a function of the temperature for both the cooling and heating cycle. And here each dot corresponds to a real XRD map. It is noticeable a marked hysteretic behavior between these two temperature cycles. And also there is a metallic and a semiconductor behavior in the resistivity near the phase transition temperature. To study how hysteresis affects resistivity during temperature cycles, device simulations using drift-diffusion model were performed. The device was modeled applying a threshold function to the XRD image in order to get a binarized one. So the so-obtained binarized image is then converted into a matrix where white pixels are coded with a +1 and black pixels with a -1. Since the edges are quite rough, resulting in a low-defined mesh, a Gaussian function was applied to smooth the interfaces. An adaptive mesh allowed to better understand the electro-optical properties at the edge boundaries of the two phases. A list of lines connecting two adjacent points is generated, and whenever a line is closed, a surface is generated. So if a surface is completely enclosed in another one, a parent-child dependency is detected. At this point, we're left with the outlines of the region. So to obtain a complete device, a rectangle with the same dimensions of the original image is created, and the black regions are located by subtracting the white ones to the rectangle. Here is an example of the device where the blue lines are the contacts, cathode and anode, and the black and white regions are the tetragonal and orthorhombic one, respectively. Since the availability of XRD maps is limited to only few temperatures and a better resolution to analyze the resistivity was needed, we developed an algorithm to generate artificial maps at any temperature, exploiting the Monte Carlo method and Ising model-based algorithm. Starting with a known configuration, namely an XRD map, domains expand following the energy minimization principle. So from statistical mechanics, we define the probability of a spin, or in this case a pixel, to be in ±1 configuration. So if a single spin or a pixel, sigma m, is to flip its orientation, the total energy would change by an amount described by the following formula, where EF and EE are the energies after and before the spin flip. J is the coupling energy and N runs over the nearest neighbors of M. If delta E is less than 0, the spin is flipped, otherwise the spin will be flipped with a probability proportional to the following exponential, where Kb is the Boltzmann constant and T is the temperature. To generate a map at a given temperature, the tetragonal phase percentage at that specific temperature has to be calculated. To do so, the amount of pixels to be flipped is set performing a linear interpolation between the XRD tetragonal phase percentages. The different dashed lines indicates the different temperature rates. It is noticeable that a slower cooling Eden cycle leads to a narrower hysteresis. So by changing the interpolation function, it's possible to tune the hysteretic behavior of the device. Drift-diffusion simulations took into account Shockley-Riddle and direct recombination. Ohmic contacts were considered in order to study only the material's resistivity, avoiding the contacts effect. Band edges have been set considering energy gap for each phase, leading to the discontinuity at the domain's boundary. Band offset due to the phase transition obtained by tight binding calculations is energetically distributed as 75% on conduction band and 25% on valence band. Mobility model is described by the following formula, with a low field model with a power law temperature dependence, where μ0 refers to the mobility at room temperature for the two phases and gamma is the temperature coefficient. This plot shows the resistivity as a function of the temperature for the generated maps. Here each dot corresponds to a different map, and the tetragonal phase percentages have been set by interpolation functions shown before. Tetragonal phase retention below the transition temperature widely affects device behavior, in good agreement with the experimental results, demonstrating the reliability of the developed algorithm. In particular, thanks to the higher temperature resolution, we were able to accurately detect the peak temperature, showing its dependence on the temperature cycle. This study elucidates that resistivity peak is ascribable to the incomplete phase transition, leading to a huge crystalline structure disorder. In fact, the proposed electro-optical parameterization as well as the interpolation function were crucial to explain this perovskite peculiar behavior. Here, we can see how resistivity varies approaching the peak temperature, as deep red increases, indicating a higher resistivity. The automatic generation of domains inside a device could be useful to shed light on different material properties. Thanks for your attention.